Now that we've finished up with one sample t-intervals and t-tests, we're moving on to two sample t-intervals and t-tests. We start to go through these chapters a little quicker because at this point you should have the basic grasp of confidence intervals and hypothesis tests, and we're just making slight changes with each chapter. As for the key changes in these inference methods, remember that anytime we have independent random variables, when we want to find the standard deviation of those combined variables, we always add the variances. So we had started off in the previous chapter by finding the standard deviation as s over radical n. Now at this point, we're going to square that whole thing. That's going to give us s squared on the top and n on the bottom because this squared and this square root cancel each other out. We would do the same thing with the second sample, and we add them together. We're adding the variances just like we did back in Unit 4 when we first went over these. That's how we find the standard deviation or standard error of the difference between two population means. Test statistic, we just take our two samples, we subtract them, we compare them to the null hypothesis value, and this is always 0, so we can really just skip writing that, divided by the standard error. And then confidence interval is always the difference between the two samples, and then add and subtract the margin of error, t-score times that standard error. Assumptions and conditions, you could probably guess. We have randomization, 10%. Since it's quantitative data, we have to check the nearly normal condition. All three of those we're checking for both groups. And since we have a second sample here, we're checking the independent groups assumption just to make sure the two groups we're comparing are independent of one another. Now, one thing that's very different is degrees of freedom. For one sample, degrees of freedom is just the sample size minus 1. For two samples, it's this really complicated equation here. So the good news is that we're never going to actually do this. We're just going to let the calculator do it for us. For our chapter example, we have two samples. We have a sample of 6 brand name batteries, and we have a sample of 6 generic batteries. We ran all of these batteries until they were dead, and we measured how long their lifetime was in minutes. The question is asking, create a 95% confidence interval to contain the true difference between those population means. Confidence interval, it's a panic question. Let mu g represent the true mean lifetime in minutes of generic batteries, and mu b represent the true mean lifetime of brand name batteries. Assumptions and conditions. Randomization, both sets of batteries were selected randomly. 6 sets of batteries are less than 10% of all brand name and generic batteries. And I'm going to skip the nearly normal for now. We'll get to it on the next slide. Independent groups, the battery lives are independent of one another. For the nearly normal condition, the first thing we look for is, are sample sizes greater than 30? If it's true, if they are greater than 30, we can say the central limit theorem applies because n is greater than or equal to 30. Our sampling distribution will be approximately normal under the central limit theorem. That's not the case here. We have sample sizes of 6. The next thing we would look for in the text of the problem, does it tell us that the population is normally distributed? It does not, which means we need to make graphs to show that this is approximately normal. So here I have 2 normal probability plots. You have to draw these. If you don't draw them, it's the same as just leaving out this condition. You can see they're both approximately straight with no outliers. Left is brand name, right is generic, and we would just state the normal probability plots of both data sets are reasonably straight with no outliers with these 2 graphs sketched out. Name the method. This is a 2 sample t-interval, just like last unit. When we add a second sample, the only thing that changes is the name, is the 1 sample changes to a 2 sample. Write the interval. So here are all our summary statistics. We have a mean for both of our samples, and we have a standard deviation for both of our samples. We would get those by putting it into our calculator as a list and running one variable stats on each of those lists. Standard error. Take s squared over n for the first sample, add s squared over n for the second sample, square root the sum of those two things, and we get 7.29. Confidence interval is just the difference of our 2 sample means. Add and subtract our critical t-score times the standard error. Our critical t-score is given to us by the calculator. So basically we put this in our calculator, we let the calculator do it, and it's going to tell us the degrees of freedom is so-and-so. Actually, I don't know what it is because I didn't write it down, but it'll say it in the output, and we can use that to look up a critical t-score. Of course, like normal, we don't write any of this. We let the calculator do all of it, and it's going to spit that out for us. Now we've obtained our confidence interval, and keep in mind that anytime we're working with two samples and creating an interval from those two samples, it's always telling us what's the difference in those population parameter values. When we write our sentence, we want to make it clear it's about the difference in those values. And since it's quantitative data, we want to make sure we're talking about means and not proportions. We are 95% confident that the true mean lifespan of generic batteries is between 2.1 minutes longer and 35.1 minutes longer than the mean lifespan of brand name batteries. These are both longer because our entire interval is positive. If, for example, this one was a negative, then this would change to shorter. Let's also go over interpreting what 95% confidence means. They could also phrase it as explain the confidence level instead of interpret the interval. If we take many samples of the same size and create an interval for each sample, we'd expect 95% of those intervals to contain the true mean difference in battery life between brand name and generic batteries. Every time we took another sample of 6 batteries, we're going to get another X bar. Okay, same thing here. Get another X bar for the generic ones, which is going to change these numbers. These numbers aren't special at all. Notice that these numbers aren't anywhere in this green sentence. All that we're saying is that if we did this a whole bunch of times, while these numbers will change pretty much every time, in 95% of our intervals, the population difference, mean difference, is going to be between those two numbers. One other note before we click off. It's important to notice that 0 is outside this interval here. So the fact that the entire interval is positive is telling us that there's a statistically significant difference in the lifespan of these two types of batteries. Same data, let's do a hypothesis test now, and let's test the claim that generic batteries have a longer mean lifespan than the brand name batteries. The parameters were defined in the confidence interval, so we'll skip that and jump to the hypotheses. Just like Unit 5, null hypothesis is always that there's no difference between our population parameters. The mean of generic batteries is the same as the mean of brand name batteries. If we subtract those two, we'll get 0 because there's no difference in between them. Alternative comes from the text of the problem. It's saying generic batteries are better. If we wrote it like this, we would have mu G is greater than mu B. Okay, we just moved everything to one side here. Okay, so we're saying the generic is greater than, generic minus brand is greater than 0. Assumptions and conditions we already did. This is a 2-sample t-test, and we want to find a test statistic. Here are our sample statistics and our standard error. So the test statistic, if we take our 2 sample results and we subtract them, is that an unusually large difference compared to the null hypothesis? The null hypothesis always says that the difference is 0. So this really isn't even there. We're just looking at the difference between those 2 samples. Okay, compare that difference to the standard error, and we get a t-score of 2.551. Now we go to our calculator, TCDF from 2.551, that's the lower, to the right side of the curve, 99 is what I use. Degrees of freedom we grab from the calculator output from actually doing the test, and we get a p-value of 0.0157. Reject the null hypothesis since the p-value is small. This last sentence is always about the alternative hypothesis. The alternative was saying that generic batteries were better, and we found enough evidence to conclude that that was true based on our small p-value. There's sufficient evidence to suggest that generic batteries have a longer mean lifespan than brand name batteries. Again, these are always about means and not about individual batteries. If you're asked to interpret the p-value, if the null hypothesis is true and there is no difference in the mean lifespans of brand name and generic batteries, the probability of seeing a difference as large or larger than the one seen in these samples is 0.0157.